infrastructure at LinkedIn. So we'll talk about the online serving infrastructure, then we'll switch and talk about the offline or A/B report generation infrastructure, and then we'll talk about the TREX, which stands for Targeting, Ramping, and Experimentation, and which is the name of our Experimentation UI, which is the entry point for all things experimentation in the company.
Sorry, Alex. Sorry to interrupt. And some audience asked you to turn off the caption, so I think that interferes. Is that possible? Thank you.
Can you see my screen again?
Yes.
Great. So this is the current state of the experimentation at LinkedIn. And at the moment, we have about 41,000 of active test entries present in our system. We serve up to 1 million of network QPS, and we perform around 23 trillion of experimentation evaluations daily. So please do not mix those with network evaluations, because those are two slightly different things and different numbers. So before we begin to talk about the infra, let's discuss what A/B experimentation is. Maybe not everyone here knows about A/B testing or joined to listen for the information for the first time. Also, let's agree on some terms. So by experimentation this talk, we will understand A/B testing, which is a scientific method of measuring an impact of some innovation or some change on a certain population. So let's say we have a target population of an experiment or an A/B test. We apply a randomized splitting process to this population, and we split it into two groups. One of them is called the control group that does not undergo any influence. And the other one is called the treatment group, which actually undergoes the influence and experiences the effect of the change. Both treatment and control in this case are called the variants of the A/B test. And the general purpose of A/B testing is to measure the impact of treatment compared to control on some metric M. Usually it's measured as some average lift plus X%. Let's go back far in time. And in 2009, LinkedIn was a pretty small company, and a lot of things were being done ad hoc. So let's imagine an experimentation user, Alice, who wants to run an experiment, and she would have to do a lot of things manually. So she would have to run an email exchange to coordinate experiment launch with other test owners. She would have to modify service configs to put experiment definition manually and push them to production. And then she would have to run an R script computing A/B results manually, and then show the results to everyone else. This is what experiment setup process looked like. All the members were split into 1,000 different buckets. And the process of assigning a member to a bucket was using this formula. The assigned bucket ID was equal to member ID modulo 1,000. And each bucket was used exclusively for each A/B test. And then inside the A/B test, the buckets were subsplit into control and treatment group. But the problem with that was that it's not a scientific method at all, because the assignment is not randomized, and previous tests could impact the results of the new tests. And that actually resulted in invalid results. The other problem was with the experiment management system. I would say it was quite chaotic, and all the test information was stored in a source control. And there was no centralized place where you would find all the test definitions. And one test could be present even in multiple places in the code base. And that complicated debugging a lot. So in 2010, a few bright minds decided not to put up with the situation and redesign and develop the experimentation infra from scratch. So they had to address the following problems. First of all, they would have to create the experimentation serving infrastructure that would be able to track test history, automatically deploy test definitions, execute tests in production, and then track and record some metrics. Then the question that we will answer in this presentation is how it's possible to scale with thousands of tests running in the platform at the same time. The second major problem was creating an A/B report generation system. And that means being able to measure, analyze, and show A/B results. So in 2010, it looked pretty easy. You just develop a big script, you throw some numbers at that, and if you need to scale, you just add more computational capacity. But by 2020, it's not easy anymore, and we'll discuss that in more details a bit later. The third problem was to create an experimentation UI so that all tests could be managed easily and people could stop coordinating via email, because emails work well when you have, let's say, 10 people or maybe 20 people in the company. But once your company grows to hundreds and thousands of employees, that's no longer efficient anymore. And creating a reporting dashboard was super important as well, so that people could see results in a single trustworthy place, and devs could see the same thing. Let's talk about the serving infrastructure. So as I said previously, it evaluates up to 23 experiment assignments per day. And by evaluating, we mean mapping a combination of a test name and member ID to some variant name. So here you could see what the devs came up with in 2010, and it already looks so much more structured. A few things that were added that are now at the core foundation of our infra. So first of all, an entity called test was created, and a test is a representation of a feature release process, starting from the point when the feature is shown to no one, or basically to 0% of the population, and all the way up to 100% of the population when it's released to everyone. And a test is a series of small ramps when the feature is gradually ramped to a larger percent of the population, and each such ramp is called an experiment. And an experiment is an immutable and versioned entity in the system. And a series of experiments essentially constitutes a test history. And since they are mutable, the only way to modify a test state is just to add a new experiment. And the code base that runs A/B testing does not have any idea about what experiments are. They always refer to A/B test by their name and not by a corresponding experiment ID. So this allows for decoupling between the A/B test execution code and the actual experiment management UI. Moreover, one more thing was added, which is a centralized source of truth of all the tests and experiments. And it actually allowed for the creation of experiment management UI. Now, let's discuss what the main principle of variant assignment is in A/B testing, because it's the foundation of scalability of the infrastructure. So let's say we have a member population, and the first thing we actually need to do is to find a way to project the member population into the interval of 0 to 1. And let's say the green member here is projected into a point with coordinates 0.08. And the second operation to do is to shuffle the member population along the same interval. And this member gets shuffled into a point with coordinates 0.85. Now, after that, we take information about all the variants in the test and their relative allocation percentage. And we split the interval 0 to 1 accordingly. So in this picture, variant A accounts for 18% of member population, variant B accounts for 40% of the member population, and variant C for 42% of the member population correspondingly. And it's pretty clear from this picture that the member point maps to variant C, so the member gets variant C. The benefits of that approach are that if you have a randomized shuffle process and you can create such a shuffle process that's independent for each of the tests, then your A/B tests will be independent of each other if you have a relatively large member population. And this thing scales well to thousands of tests running the system at the same time. The first way of assigning the member population is based on the random number generator, and it works in the following way. When a request comes in, we evaluate request using some RNG object, and we store this generated variant in some database. So when subsequent request comes in, they have to read from the store and use the variant. And I've estimated that in order to keep just 30 days worth of variant assignment data at LinkedIn, we would have to keep an online store of 24 petabytes in size. So that's pretty costly and expensive. And we actually use a different variant assignment method. We use a hash-based one. So it's based on a hash function that takes two parameters. One is the member ID, that's the first param, and the other one is the test ID, which can be, which is any ID distinct, unique for a given test, or it can be a different ID even for each of the experiments within a test, depending on what you want to do. And when a request comes in, we hash the member ID and the test ID, and we generate the variant assignment, and we don't have to store it anywhere because this function is deterministic and it's a pure function. So we can always reuse the results over and over again, and we don't store any intermediate information. So the hash-based assignment is actually pretty good for scaling your A/B testing platform. First of all, it uses less disk storage. So we only use 200 GB of an online database to perform targeting functions when you need, for example, to only run experiment only on the US population or maybe on Belgium population. And that's around 120,000 times less than would have been required for the RNG method. And it also puts less disk pressure. So again, by doing back of the envelope estimations, I kind of received these numbers of having 325 times fewer reads down to with our online store and around 3,200 fewer writes being done to the store. But does it help solve all the scalability problems in the experimentation infra? Probably not, because 24 trillion evaluations per day is quite an impressive number, and it requires you to think about the infrastructure as well, and doing some other things to be able to handle the load. This is what the experimentation serving infra has looked like starting in 2010. Well, maybe with just a few minor changes. There's an experimentation management UI that manages the contents of the experimentation source of truth. And then we have an experimentation backend, which is a service distributed on, I think, somewhat 1,000 different nodes in our data centers. We also maintain a member attribute store, like I said, for targeting functions. And whenever a service wants to run A/B testing, the devs would have to integrate two libraries into the service. One of them is the experimentation client, and the other one is the experimentation engine. So the client and the engine are just abstractions for handling all the evaluations and returning the results back to the service. This is what the request processing looks like in cases when you need to run an A/B test. So let's say there is a service that has some business logic inside, and when a request comes in, business logic handles it, and at some point of time, it asks the experimentation clients to return the variant name for each corresponding test name and the member ID. So the client then has to figure out whether this evaluation can be done locally. So if all the data is present and all the properties required for evaluation are provided, or the data is cached in memory, then the experimentation engine handles the evaluation locally, and it serves the request in only a few microseconds of latency. And what's interesting is that 99 to 99.99% of all requests within a given service are processed locally. So that's pretty fast. And for the rest of 0.01 to 1% of requests for each of the service, they go to the experimentation backend. And the backend has an in-memory cache of member attributes. And if for a given request, the attributes are present in the cache, then the backend passes the request to the experimentation engine. And the cache hit ratio here is pretty high as well. So it's 93%. And if we hit the cache, the latency is around, the total latency of evaluation is on the order of 1 millisecond. And if we have to query the store, the latency goes up to about maybe 2 to 3 milliseconds on average. But in 2017, we actually understood that you have to continue evolving because things that worked normally before no longer work when you have a lot of services running your code. We've encountered a bottleneck with the experimentation engine. It's essentially a library that does one thing, but does it really well. It takes an experimentation domain-specific language, and there are 4 different programs written in the experimentation DSL over here with the following structure. So there's a keyword ID that depends all the code, and then there are pairs of targeting conditions, and then variant assignment configurations. So the first DSL means that we target the entire population of LinkedIn, and we assign 25% population with the treatment and 75% with control. And for example, the second DSL means that we put 50% of students into the treatment group, 50% into the control group. And the second clause over here means that we put 25% of job seekers who are not students into the treatment group, and the rest of them go into the control. So going back to the topic of the scalability of the experimentation engine. At that point of time, we had around 19,000 test entries running at the system concurrently. And each of the instances of the experimentation client, basically on every service box, was occupying around 230 megabytes. So if you multiply that by the scale of LinkedIn data centers, that's on the order of petabytes of memory being used. And the engine was actually causing pretty high GC pauses because it was generating a lot of temporary objects and retaining them long enough for a GC to have a long hiccup. And at that point of time, we handled around 1 trillion of evaluations per day. So it called for an improvement, actually, because the engine was bottlenecking some of the services, and the services could not scale without improving the performance of the engine. So in 2018, we released the new engine, and our original goals were having the same execution speed around 10 microseconds for evaluation, improve memory usage, and we did not put any goals because it's hard to predict how much of memory usage you can improve, And we did a number of things. So we stopped most of lazy evaluations in the engine. We stopped using reflection APIs, and we started using compile time-generated code heavily. It was around 3 times faster than reflection. We started using packed in-memory structures for evaluation trees. So instead of storing child lists in an old object, we moved them to a single array that was shared for all the nodes per the tree. And it also improved the speed at around 3 times. And the most interesting thing we did was to create a test generator that was inferring test cases for the DSL by just looking at the structure of the current DSL programs in production. So as a result, we received 20 times faster sequential evaluation, around 15 times better concurrent evaluation speed, and we improved the memory usage about 10 times. And we also ran about 8 billion of tests to just prove the correctness of the DSL, because it's a program and it has so many different states. So we had to compare the old and new one versions of the engine. And we actually used a Hadoop cluster to perform so many evaluations. And that helped us to scale further, because by 2020, we've already had 25 times more evaluations than we had in 2017. Now, let's talk about the A/B report generation infra. It actually processes around 20 trillion of records of input data per day. And we have 3 main data sources here. We have variant assignment data, we have metric data, and we also have member attributes that help us to understand the impact of experiments on specific parts of the population. And as I said before, A/B report generation was super easy in 2019 when A/B results were manually computed in R. But by 2012, we've had a pipeline working in Pig. And at that time, it seemed that you could just throw more computing power at Pig and it would just handle everything. But by 2020, we actually processed 400 times more data. And I've estimated that we run the pipelines around 99 times faster than in 2012. That's pretty amazing, right? And here's what our input data sizes look like. They are on the left. The assignment and metric data both experienced high growth. So 23 times, we processed 23 times more of the assignment data and 8.5 times of the metric data compared to 2014. And A/B report generation requests are also much larger in the size. So we will process around 3.5 million of A/B report generation requests this year. So that's a pretty high number. In 2014, as I said, we had a pipeline working with Pig, but we started realizing that Apache Pig has reached its scalability limit for our goals. And there were the following problems. So first of all, there was no cube operator, and A/B report generation is essentially a generation of a huge OLAP cube, especially when you need to slice and dice to understand the impact on specific population cohorts. And it was prone to data skews. Some nodes would take 1 or 2 orders of magnitude more time to process the input than the rest of the nodes. Also, the other problem was that we've had a lot of data, even at that point, and it was pretty common that the data was not fitting into memory, and it was frequently spilled into disk and read back, and that slowed us down drastically. Also, Pig execution plan was splitting the join into multiple jobs, but it was doing that not at the right point. So it hindered our performance as well. We also experienced high volumes of intermediate and materialized output. So that's proportional. The output size was proportional to the total number of members in the experiments times number of experiments running in the company and times number of metrics. So that's around 2-3 times orders of magnitude larger. So again, that was pretty slow. So what we did, we developed an in-house data processing language that was open sourced in 2014. And if you'd like, you can actually read about language here. And it featured efficient join structures as well as efficient all-up queuing. And data was cleverly partitioned to avoid skews and to fit into memory. And let's compare the execution plans of Pig and Qbert to understand the difference. So this is what the Pig join looks like. So Pig uses reduced side joins. So let's say there's variant assignment data, metric data, and then test computation requests. They're partitioned and sent to the reducers. They're partitioned by member IDs and sent to the reducers. Reducers would then join the data into large rows, materialize the output, and then start processing with a new MapReduce job, which would load all the data, shuffle it again by the grouping or sorting keys, load into reducers, and then reducers would produce just a few megabytes worth of output. And the problem was that the data size exploded here, and it was super slow. So at some point of time, we've ran a job on the full size of input and output, and it took us over 40 hours to complete. And that's really unacceptable. And that did not allow for very good experimentation speed. So what we did instead was a different way of partitioning. Let's say we have metric data with this 10 terabytes of metric data with the following schema, which is metric name, timestamp, member ID, and value. So we shuffle the data by member IDs, so no changes from Qbert here, but reducers would, instead of generating a single partition, subsplit the data into multiple blocks. And the blocks were actually restricted by their size. So when the reducer was reading sorted member data over here, it would stop at some point of time when the block size limit was hit. And they would then sort the data on a different key, which is metric name and member ID for the metrics, and experiment ID and member ID for the experiment assignment data. And that actually allowed for a very efficient join. So instead of shuffling the data and joining it on the reducer side, we would create mappers, and each mapper would load corresponding co-partitioned metric and variant assignment data, join most of the things in memory here, produce very little output, and then have the reducers to do the rest of the job to aggregate the smaller data. So what was being done is that the split of the execution plans that happened in Pig somewhere in the mapper process, corresponding to the mapper process, was happening before. So that allowed us to optimize the shuffle size and execution speed. This is what join process looked like. We would load all the metric data in memory. And given that the metric data was sorted on metric names, it would be subsplit into smaller blocks corresponding to each individual metric. The assignment data would be streamed, and it does not have to be stored in the memory, and it would be subsplit into experiment sub-blocks again. So then we are doing a join of each experiment sub-block with each metric block. And when you're joining two pairs of blocks here, it's essentially a merge join because both of the sub-blocks are already sorted on member ID. So if you'd like, you can read more about this in the Qbert documentation link that was available earlier or will be on the reference page at the end of the presentation. But it helped us to speed up our computation somewhat 6 to 8 times. And that was a very good result. So our report generation latencies were back to normal of maybe 4 to 5 hours for some time. By 2016, we realized that performance of the pipelines is important, but when you have a lot of A/B report generation tasks, and you have to process different types of experiments, different types of metrics, the pipelines just become unmanageable. And there were a few problems with that as well. So first of all the pipelines were monolithic. And it meant that either you run the pipeline or you not. So if it breaks somewhere in the middle because of intermittent failures, then you have to restart it and wait until the full computation completes. And as you all may know, that Hadoop is sometimes fairly unstable. And what would mean essentially a single request timeout in an inline environment, or something that could be rebalanced when being served from a live service. In inline pipelines usually mean failure because there's no rebalancing of jobs. The other problem was that, as I said, they were hard to manage because they required manual restarts. And when you have a few dozens of pipelines, it starts taking a lot of time already. And every pipeline was processing the data from multiple data sources, and each of the data sources had different cadence of updates. So metric data could be updated 600 times a day because we have somewhat 600 different metric data sets. But the variant assignment data is only ETL'd and processed once per day. So essentially, we could not generate metric faster. We were bounded by the frequency of the variant assignment job. And it was actually pretty inefficient resource usage because if you upload data to a database, then you cannot continue using your Hadoop queue and you're underutilizing your resources. So what we came up with was splitting the job, such monolithic jobs into multiple jobs based on their resources being used and also on their frequency. And here you could see that instead of having one job that does it all, we have variant preprocessing job that runs daily. We have a computation job that can run as often as maybe 30 times or 50 times daily. And then we have a separate result uploading job that requires access to Pinot and MySQL databases. And that, as I said, we decoupled the stages, we decoupled the usage of different resources, and that helped us even with self-healing, because once you split the jobs, you can make them self-heal and restart every so often. In 2018, something remarkable happened. We've actually tried Apache Spark, and we found out that by simply switching our computational code over, we could save around 40% of computational efficiency without even porting all of the improvements that we did in KubeVirt. And the efficiency here is measured in GB hours. Just for reference, this is the number of pipelines that we have at the moment. So we have around 180 different pipeline instances that process over 20 trillion rows per day. Most of them are trigger-based and split into multiple stages working independently. And we use loose coupling and reuse component via a messaging system. So we have a very advanced scheduling mechanism there. And this chart shows us our efforts at keeping the computational load at bay. And as I said, we have about 400 times more data compared to 2014. Unfortunately, we don't have execution times from 2014, but this is how we scaled and how we kept our report generation latency small. So that's I think that's a pretty good job to be able to reduce the time from 16 hours to around 2-3 hours, and then keep it about at the same level for multiple years. And at the moment, we run on average 736 A/B tests in the A/B report generation pipeline, and we compute 7,900 metrics at the same time. Now, let's talk about scaling of Experimentation UI. I know it may sound a bit unexpected, but let's discuss what scaling the user experience means. So we think that scaling of experimentation UX equals to scaling decisions at the company and improving their speed and quality. And there are three things you could do to scale the decision making. First of all, pay more attention to collaboration because it gets more complex with the growing number of participants. And if you do not organize or structure the interactions between people, they will grow as big of n squared of the number of participants. And collaboration also means simplifying connections between multiple actors in the system or between multiple roles that people have in the system, like interactions between test owners and stakeholders, or interactions between developers, data scientists, SREs, and PMs. The other part of scaling the decision-making is about improving productivity of each individual person, of each individual participant of A/B testing, and improving the speed of failure detection, decision-making, and speed of A/B report analysis. The third pillar is about improving intelligence of the system. Because once you start having more data and once you start having more metrics and tests, people will no longer be able to analyze all the data and will not be able to find all the patterns manually. It's also about suggesting the right actions based on the full set of data available, because people can only reason about a very small subset of the information available to the infra. It's also about preventing mistakes and making sure that people do not do unrecoverable mistakes that will result in data loss or maybe in revenue loss or loss of the member trust for the company. So one of the examples of improving collaboration and scaling decision-making was the introduction of the Experimentation UI in 2010. As I said before, people had to send emails to each other. All the test owners had to send emails to each other. And it was a quadratic complexity of the number of participants. But with the inception of the UI, people would only have to interact through the UI. They would see the same data, and the UI would suggest to them whether there's any interference or other tests are running and whether they can start their experimentation. And this is what the growth of the number of metrics available for computation in the experimentation system looks like. So it's 16x more than what we had in 2014. And you could imagine it's just a full ocean of data. So we've had to deal with that problem as well with the metric growth. In 2015, we have noticed one pattern. We realized that there are test owners, but test owners usually use metrics created by other people. And other people would be interested in having their specific metrics either grow or stay, better grow. And sometimes they would be surprised to see why their metrics were dropping. So we developed a product called Most Impactful Experiments that would connect experiment owners with the metric owners and show experiments with the most positive or negative impact on every specific metric. So I think sessions and revenue metrics are just fine over here. Everything is positive, but one surprising fact could be for the owner of page view metrics that experiment 4 should probably be deramped because it affects important metrics in a negative way, but experiment 3 is actually doing something to improve the metric. So that was a very good information to surface. In 2017, we've also introduced another concept, which is the concept of tier 0-1 metrics, and which was about standardizing metric data sets. So just imagine having to deal with a few thousand of metrics. If you run a test, you would probably only look at the metrics that you are interested in particular. So maybe a few dozen or 100 metrics at most. But now what we are doing, we are actually grouping most important metrics into two data sets called tier 0 metrics and tier 1 metrics that are shown by default to every test owner when they open their experiment. And every test owner is aware that those metrics are very important to the company, and they should always be, should only be growing. In 2018, we also realized that the experimentation process could also be improved because there were lots of tedious tasks being done by people, and the people were doing ramping from 0% to 100% inefficiently. We counted there were around 338 unique ways to ramp in 2018, and people were taking too many steps, from 2 to 100 steps to ramp a single feature. That looks pretty inefficient, right? And people were spending 2 more weeks on average to ramp a feature than they should have spent. So that was ripe for improvement. And we've actually developed a service called Ramp Assistant that takes A/B test results as the input, and it makes an automatic decision to ramp the test up, ramp it down, or submit for a manual review by a human. And this ramp assistant is based on a framework called SQR, which stands for speed, quality, and risk. And the information about the paper that it's based on will be available on the reference page. So just to summarize, let me maybe reiterate things that helped us to scale. First of all, for the online serving infrastructure, it was choosing the right method of the variant assignment. Second thing that worked really well was to use extensive caching. And in our case, we use at least 2 layers of cache. Maybe something else is present in the data layer storage, but 2 layers of cache does a pretty good job for us. And the other thing was investing into the performance of our stack. For the A/B report generation infra, this was investing in efficient join algorithms, using trigger-based and message-based computation, and switching to Spark. For the user experience and intelligence part, that was about simplifying collaboration, automating as many things as possible, because, well, every person in the company runs A/B testing, and improving the signal to noise ratio, generating actionable insights. Thank you very much for your attention. And if you're interested to learn more about some specific parts of the system, please check out these papers and blog posts. And please let me know if you have any questions. We're taking questions via the Q&A section in Zoom.
Great talk. Alex, there's about 6 questions on the Q&A site.
Okay. So let me read the questions first aloud, and then I'll be answering them. So could you talk more about the motivation behind eliminating lazy evaluations in the new extension? Is the alternative pre-computing all the targeting and variant assignments? The motivation was that we were using, in the V1 of the engine, we were using Clojure, the Clojure programming language, and the code was heavily based on the lazy evaluations. So I don't think it's a failure of Clojure. I'm not going to blame the language, but we've noticed that lazy evaluation structures were taking a significant part of the heap, and by getting rid of them, we would reduce, first of all, the heap allocation. I think it dropped around at least 4 times after we killed all lazy evaluation structures. Second, we also were concerned a lot about the performance, given the engine was bottlenecking things. And we've tried to keep only bare minimum of things. All lazy evaluation things require functional calls, function calls, virtual method invocations, and so on and so forth. So we've switched to simple for loops and evaluations in the most critical parts of the stack and the code. And as you have seen, that worked really well for us. So the second question is from Gaurav. What is the definition of an experiment? When it mentions 35K simultaneous experiments, does it mean that there are 35K deployed product changes iterations, or there's some sort of automation also involved? So first of all, what is the definition of an experiment? Like I said, an experiment is a particular ramp stage. So it has a fixed allocation of population to an experiment. So fixed percentage allocated to each of the variants. So like 50% of population allocated to the treatment, 50% allocated to the control. And the definition actually contains a few things. So first of all, it contains the DSL program, which tells the Elixir engine what population to target and what variants are assigned to the fractions of the population. It contains information about the hashing ID. So we can change hashing ID with every experiment if there's such need. And it contains some service information like activation date, possibly termination date, but the production only has active experiments, so it's essentially about only activation date. There are 35,000 test definitions in production, and some of them are active and running A/B tests. So the thing is that some iterations are controlled by people, and some iterations take longer to ramp. Some iterations sometimes get abandoned. Some iterations are never intended to ramp completely. So they can be used as some sort of dynamic configuration specification. So you could use the experimentation engine to split the traffic between different data centers. There's some automation involved. So we have services creating A/B tests, thousands of A/B tests, and then terminating them per day. And that depends on what you want to achieve. So you can create a test manually and go through all the stages of experimentation manually. You can write a service that would create a test automatically for some purpose, like for a load test, and then gradually ramp traffic to hit a specific host in the A/B test. And you could do a lot of things with that. So I hope that it answered your question. A question from Nathan, planning to open source T-Rex. We hope we can open source it, but it's honestly a lot of work. There's a lot of work involved. The system and the platform has evolved for over 10 years, and we cannot give any specific dates about open sourcing. How did you scale experiment debugging, for example, in the case of sample ratio mismatch? So we detect, so whenever there is a sample size ratio mismatch, we show the information on the UI, and I believe we will be, or we are already sending notifications to users that there's a mismatch, and we have a specific data pipeline that analyzes all the data available, and it categorizes a specific case of sample size ratio mismatch into several different possibilities. So it doesn't always detect what you're looking at, but I think it works well in somewhat 90% of all the cases, and the rest 10% of the cases need to be analyzed manually. Also, the experimentation engine writes some information to the log, to the services log. If anything goes wrong, we produce operational metrics that are available for debugging. And we also have a huge data set with tracking information with variant assignment. And we are able to get down to the host, service, and container level and understand what events it was sending. And yeah, we try to have reasonable amount of debugging information available. How do you determine which metrics are relevant for an experiment, given that there are thousands of metrics to choose from? So the first and foremost, we have tier 0 and tier 1 metrics. And these are the metrics that the company as a whole cares about. And every test owner should understand that if there's negative impact to tier 0 and tier 1 metrics, then it should be justified by maybe overwhelming positive change of something else. So maybe one tier 1 metric is dropping a bit, but the other one is going up significantly. The other thing is that test owners usually have to identify their success metrics before even starting the experiment. So a good experiment design process actually involves defining your goals and your success metrics and maybe the expected lift for success metrics. So then when you run an experiment, you have to look at tier 0 metrics, tier 1 metrics, and your success metrics. And if anyone else cares about some other metric and it gets negatively impacted by your experiment, they will come looking for you and they'll discuss with you whether the potential negative impact on their metric is justified. Does LinkedIn do experiment targeting on entities besides users, posts, pages? To some degree, yes. Most of targeting capabilities are available at member level, but there are some other things we can target on. So for example, we can target on some, let's say, company properties or some pages properties. So that's a capability that we have available in the system. Does having different assignment rates to treatment and control for different segments introduce bias, or is this being handled in the experiment evaluation logic? So the thing is that when we apply targeting conditions, we have one implicit assumption here that the targeting condition is independent of the variant assignment. So basically, if you run some process maybe on Hadoop and you generate targeting condition that only targets members in the treatment group within a specific test with a given hash ID, and then you load this attribute into the system and you put that as a targeting condition, then it will be natural that your specific segment will not be getting any members in the control group. So you can introduce some bias or you can introduce sample size ratio mismatch, but usually that does not happen. And also just going back to the main idea of the variant assignment process, we apply a randomized shuffle process and randomized assignment process to get members assigned to a given variant. And that means that a lot of, differences and discrepancies between the member groups are eliminated. So in some cases, there are outliers that skew the experimentation results. But again, if you have a pretty large member population, even the outliers may even out and you get fairly precise and valid results. Do you have real-time metrics for experiments? We do not, because we have a few billion of evaluations per day, and we've had an attempt at creating real-time metrics at some point of time, but we realized that this SAMSA pipeline was actually taking pretty heavy computational load, but it was failing to generate results with enough statistical power. So we are looking at the ways how to improve this and whether we can actually generate real-time metrics, but at the moment we do not have a real-time A/B testing pipeline. We are also planning to introduce multi-armed bandits and adaptive A/B testing, but it's not there yet. Follow up to the experiment scale question. How do teams of human data scientists analyze 3 million reports? That's a very good question. And as I said, some of the interactions happen via tier 0, tier 1 metrics. They are always being analyzed success metrics and most impactful metrics. However, some of the metrics are being used only locally, let's say within a given test or within a given experiment. And at the moment, we generate all the metrics for all the experiments, but we are planning on cutting down the load and generating only what will be used and what people want to see or what people have defined as their success metrics or importance metrics. We will stop generating some metrics that are not frequently used. Also, if someone still wants to create an A/B report readout with some of the metrics that were previously unused, they can run A/B report generation on demand and get an ad hoc A/B dashboard.
I think that's all the questions, right? Okay, great.
Actually, in the chat, there are 2 questions I asked on behalf of somebody else. Maybe you can just take a quick look at to see. It's in the chat.
I see.
LinkedIn is known for handling experiments on social graph, splitting into clusters of people who know each other, and minimizing contacts between control and treatment. Do handle that. This is not a core capability. It's actually done via targeting attributes, and it was a project done by our data science team. This is handled via an offline process that splits out or partitions members based on their proximity in the social graph to each other, and then it's loaded as a targeting attribute, as a set of targeting attributes into the system. So you can actually run such experiments, but it's just done in a different way than the rest of the experiments in the system. So I think there are some posts on the engineering blog at LinkedIn about such experiments, and I think there could be also a paper about doing that. And there's a lot of information even about project every member, about making sure that there's even impact on all the social strata for all the members and all members benefit equally. So please check out the engineering blog. I do not have the links handy, but some information should be there. So how do you manage report out conflicting metrics? Experiments A to E help increasing metric M, while experiments F to K might decrease it. So this is what most impactful experiments functionality is for. So again, usually metric owners are the people who care about the metric, because if no one cares about the metric, maybe it should just be removed from the system. Experiment owners may be unaware that there's some underlying story going with their metric, and they may be unaware that there are some experiments that may be helping the metric to grow, but some other experiments may be pushing it down. So it's metric owners' responsibility to go and figure out what goes wrong and understand whether the experiments that push the metric down are justifiable.
I think you had one more question on the Q&A side. I hope that's the last one.
One thing I'm also curious about is the logging of the user exposures to the various experiments, specifically with the Lixis local check-in. How's login handling? Is there some local caching to reduce network traffic? So we do, by the way, there will be an engineering blog about that, and it will talk about such thing in greater detail. Please connect with me on LinkedIn. I'll be advertising such links. We log variant assignment. So we do not store variant assignment for subsequent evaluations, but we log them for A/B report generation to improve precision of the cases. And we only retrieve the variant assignment in some jobs. variant assignments are logged via Kafka, and there's a limit. There's a limit until which you can actually send events to Kafka, because after that the cost to serve becomes too high. So let's say if there's less than 1 billion events generated by service in a given experiment per day, or maybe less than 5 billion, just some random sorry, some random number, then you can log it to Kafka. If your events go to 100 billions per day in the count, then we are actually asking the teams to stop reducing events to Kafka and switch to what we call targeted experiment computation. So instead of using the log tracking events, we stop we stop emitting Kafka events for a given experiment, and instead of we use page view data for a given day. So we take all the IDs from all the users who had a page view during the day, and then we replay the variant assignment process on that. So one more amazing thing about the hash-based assignment process is that it's replayable. So you can take some data and then you can run the assignment post factum. And then we just take this post factum generated data, push it into our pipeline, and then we have somewhat a number of million of IDs pushed into the AB generation pipeline, and we use such IDs. So that works really well for experiments that really target all the users who visit the site at any given day or are very close to doing that. If your experiment really triggers fewer members, then at some point of time, it may benefit to switch to Kafka login to know precisely who has triggered a given experiment and use this knowledge directly. I hope that answered your question.
I think that's all our questions. This is a great talk. Oh, somebody just posted another one. Oh yeah, the slides, he's asking whether the slides are available or not.
Hi, James. There will actually be a blog post coming out. Let me actually switch to the first slide. There will be a blog post coming out, and there will be also an article about things that I've spoken here about, but at greater detail. So please connect with me at LinkedIn, or just follow my account. I'll be posting some links about A/B testing at LinkedIn periodically.
Yeah. Also, the recording will be available after the talk, and I'll share on the San Francisco Big Analytics YouTube channel. So I'll be posted there. I'll also post on the Meetup page as well after I got it. Okay, great. Thank you so much, Alex. This is a great, wonderful talk, and I haven't had this kind of a talk for several years now. This is the first time I see the talks on the infrastructure for experimental platform. So thank you so much. Yeah. Okay, thank you, everybody.
Thank you very much. Thank you, everybody, for attending the talk. I really appreciate that.
Yeah, so thanks, Bill from the AI Camp for helping us set this up. Thank you, everyone, for attending. I'll see you next time. Okay, bye-bye.
Bye-bye.